Professor Ooi, can you switch on your video now?
Yeah, now I think he's.
Yeah. Okay, so Professor Panika, should we now start? So I can.
Yeah, I think. Yeah, good morning, Professor. We can start. Good morning.
Good morning, Professor Ooi, and welcome to QIQT, fourth day of QIQT. We are extremely happy to have you here, and I welcome everyone to this fourth day of QIQT 2023. And we have a session as usual, like other days. And we are extremely happy to have Professor Raymond Ooi from University of Malaya, Malaysia. Let me quickly introduce him, and then we'll hand it over to Professor Ooi. So our first speaker is Professor C.H. Raymond Ooi. He's a professor in the group of Quantum and Laser Science, Department of Physics, University of Malaya at Malaysia. He has been an elected fellow of the Academy of Sciences Malaysia since 2015. During this time, he was also a visiting scientist at Princeton University and Max Planck Institute of Quantum Optics. His research interests lie in quantum optics, nonlinear molecular spectroscopy, and quantum microscopy, statistical physics of B condensates, interactions, generation, and propagation of ultra-short and intense laser pulses. In 2011, he joined the Quantum and Laser Science Research Center and developed the ultra-fast high-intensity femtosecond laser and optics facility. Recently, he has been leading a quantum communication research program in Malaysia. And he has a very intriguing title of the talk, basically on molecular Raman quantum memory. So without any further delay, let me hand it over to Professor Ooi. And yeah, welcome to QIQT 2023, Professor Ooi. And please, maybe you please upload your slides and go ahead. Is your microphone on, Professor Ooi? Can you share your slides? Professor Ooi, can you share your slides? No, we cannot see your slide, Professor Ooi. Can you also speak? I cannot also hear you properly. We can't see your slides. Also, can you speak because we can't hear you?
Hello, can you hear? Can you hear me?
It's a little weak. Can you speak? Because we can't hear you.
Can you hear me now?
Yeah, we can hear you. But you have to share your slides now.
Okay. Can you see my screen now?
No, it's not coming. Can someone help? Is anyone here? That because the slides are not getting shared.
Okay, sir. I think it is sharing the screen, but he uses Chrome. We have to share the slide.
I think so, sir is sharing the entire screen rather than the slide because we could see his screen.
So should
You can see my home screen,
Professor Ooi,
right?
can you share? So should you share entire screen or the?
Can
But
you see my
now
home
I think it
screen
will
now?
come. Let's wait.
Can you see my screen now?
Not yet. So have you opened your slides? Because we can see your basically we can see you in the background, but
Uh,
Subhimal or anyone around here?
Yes, sir. I'm
So
there.
can you suggest, because I think there is a problem whenever he is trying to share, basically my screen is somehow coming. I don't know why. Does he have to share this?
Yeah, I hope your screen is not shared.
do I go
Obviously
to
not.
do I go to window entire screen?
So does he have to share entire screen or?
He can do it either way.
Yeah. Now it
Yeah.
has come.
Okay,
Now
okay,
we
now
can
we
see it.
Sorry,
Now we
Now,
can see
okay.
it. Yes.
All
Yeah,
right.
you can make full screen, and then yeah, it has come now. Okay, so everyone, so we may start now because yeah,
Okay.
already. Let's say Professor Ooi, you may proceed.
All right. I will go on now. Sorry for the delay. So today I will talk about quantum memory with molecules. Let me start by introducing some aspects of quantum communication. We are trying to build quantum network, and some of the ingredients are quantum repeaters. We need a trusted network, and quantum memory is the important part of the whole network. So we need quantum memory to synchronize and store information for up to say hours, and this so that we are able to show the coherence through the interaction with environment, and then we can store the information, and we can release the single photon on demand. There are several candidates and schemes, type of material also that have been actively explored in the community right now. And this is the main bottleneck for developing quantum network. Currently, there are a lot of commercial quantum communication products are already.
Hello, sir.
Yes.
You have to make your slide full screen.
Yeah, it is.
Slides are not in the full screen mode.
It is full screen.
No.
Make it full screen. So it is, otherwise it is showing small.
Okay.
Make it
Go
full
to the
screen.
slideshow.
Yeah, so that is there.
How about now?
Yeah, that is.
Is it full screen? Okay. Yeah. All right. So many quantum communication products are available in the market now, especially in IDQ and some other companies around the world. If you want to go for long distance communication, we will need quantum repeaters, and there are also some proposals which are repeaterless, and it has been demonstrated that this is also quite a promising approach. But we are dealing with material quantum memory, where we will store information in the material and then we retrieve quantum information later on. And the technology mainly make use of state-of-the-art ultra-low loss fibers, and the emphasis is on high repetition rate up to gigahertz. And the detector side is most challenging because we need to detect single photons. So we have to use a superconducting nanowire photo detect single photon detectors. Compare current network. This is a current classical network with quantum network. The current classical one is not secure, and the quantum is supposed to be unconditionally secure, making use of quantum effect like entanglement and superposition of states. Physical eavesdropping is be possible in the current fiber communication, while in the quantum case, eavesdroppers can be detected. The resource is there are a lot of resources available in the classical, and while in the quantum case, we hope that something is we can develop the technology that is more self-maintaining. For the classical is most probably hackable, but for the quantum is fundamentally unhackable. And the quantum case, we have making use of the superposition of 0 and 1. For the amplification of signal in classical case, we use amplifier, while in the quantum case, we use entanglement swapping is most promising so far. So current challenges in quantum communication is that entangled photon have to survive long distance fiber, and long distance entanglement in order to achieve that, we need quantum repeaters and quantum memories. So it is difficult to store information in matter because of the decoherence, the problem of decoherence. And there is currently many schemes, many approaches have been proposed. However, there is no single protocol or technology that fulfill all the performance criteria to become a viable quantum memory. So if we can integrate quantum memory with optical fiber and with a very efficient conversion between optical photon and telecommunication photon, I think we are getting closer to quantum communication network using the existing optical fiber infrastructure. These are the main quantum memory. Standard one they use atomic ensemble, core temperature, and also room temperature. Room temperature is more challenging, but it's also more practical. In the case of solid state, many sub candidates have been explored, spin crystal, Trojan vacancy diamond, and also rare earth crystal. These two are quite promising, but one thing has not been explored is a molecule has not been widely explored. There are some works being done, so we would like to explore the molecular aspect here. So hopefully we finally come up with a scalable quantum memory that is fault tolerant and error free, and also unconditionally secure. We need to consider the performance of the quantum memory, these are the main performance like we need to have long coherence of storage time, high efficiency, because we are dealing with a single photon or few photons, so efficiency is extremely important. And also quantum information, we need to make sure the fidelity is high enough to preserve the content of the information. At the same time, there are many competing processes happening, so there are a lot of noises here. Practical noise and also fundamental noise, we need to take care. This is both fundamental and technology. So we need to have low noise to avoid any error, to reduce the errors. And also very important is to have a large bandwidth multi-mode capacity so that we can store a lot of information in the photon and transmit it. And as you know, bandwidth is related to the pulse width. So if we want a fast repetition rate, the pulse has to be short. So if the pulse is short, then the bandwidth will be wide. So that's why it's important to have large bandwidth if you want to go to high key rate. And scalable, we need to be able to scale up the quantum memory. Okay. And these are some of the numbers that have we got from literature. So it may be a bit old, but we can use this as our comparison. So this is a summary of a table of existing quantum memory materials, alkali gases, solid state, diamond, that negative frequency diamond, also neutral frequency diamond, as well as rare earth crystal. And for storage time, this solid state material is more promising, can store up to hours, provided they have some techniques like dynamical decoupling you can employ here. And also the noise materials for solid material, there is not much contribution to significant noise, but in the gas, there are these competing for mixing process. For the temperature, normally alkali gas for the warm room temperature gas is possible, but if you go to ultra cold, the setup will be more complicated. For solid, we need to cool down to cryogenic temperature so that we can harness the narrow line width of the transitions. So it's necessary to have close to 1 Kelvin or below. And scalability, the solid is definitely more promising. And all the schemes can be used for this use these materials, except EIT. EIT will need a narrow line width, so it's not possible. And these are the main existing quantum memory schemes: EIT, Raman, off-resonant cascade. CRIP is a method that makes use of the electric field, tuning of the electric field, and gradient echo memory. Also, AFC is interesting, is making use of preparation of series of pulses to achieve comb in the population. So each one has its own advantage and disadvantage. We need to try to understand what are the advantages of each scheme, and maybe we can come up with something that works better, maybe a hybrid. Okay. In here, we would like to consider a unified quantum framework. Theoretically, first for molecules, and maybe we put it in a cavity, and we put some structures so that it will be able to control the quantum effects in the cavity. And we want to also use a quantum memory as a converting, also to convert between the telecom and the optical regime. So we are currently studying this using a simple density matrix formalism. This is some preliminary result. We want to see if we can preserve the coherence. So now our focus here is more on molecules. Is because why do we study molecules? A lot of people would think that, oh, there are many levels in molecules and it will be more complicated and will give problem. But actually, our human body itself is a wonderful quantum memory. We are inheriting a lot of information, memory from the past, evolutionary memory. So molecules could be good information storage, but how do we manipulate it? How do we make sure the coherence is not standing in the way? So here are some of the advantages of polyatomic molecules. It may be simple one first, simple molecules, and this is one of the examples. But our DNA is a wonderful quantum memory. So extremely flexible, we can synthesize organic materials at low cost, and also this molecule can support different memory storing schemes over a wide range, from infrared to optical range. And the quantum coherence that is formed, it will be different from the atomic case. It can be a small position of ground vibrational levels. So it will automatically give rise to multi-mode broadband storage capacity. Photon memory at terahertz rates may be possible, which means we can have shorter single photon pulses. And this can be designed, can be tailored to become something very functional. And also thermal and chemical stabilities can be improved. Hopefully we can improve this, make it more stable against environmental changes. Okay, and this is, if we study this, it can also help us to understand evolution and life. All right. So there are some existing work in this paper. They have been studying coherence time with of this molecule. The zero phonon line is important to detect, and this is quite some time ago. And then more recently, we have more relevant to this work is more relevant to quantum information processing. They have used, they have been able to store some information in using the read and write protocol in hydrogen gas, hydrogen molecules. Then the vibration level would be in the order of from 0 to 1 would be in terahertz. So they got efficiency of 80% and 51 compared to 51 predicted efficiency. And their write efficiency is nearly 30%, read out efficiency is 60%. And they're avoiding the excited state by using off Raman. So in molecules, it's important to avoid the excited state. Otherwise, the spontaneous emission of fluorescence will create a lot of noise. They go to many levels. So this is a very good wide bandwidth, and it can store up to the 100 femtosecond. Okay, and operational time being will be 10 to the power 4. So this is promising work. Another work is on the coherent properties of single molecule for quantum network. Is studying this macromolecules, very big molecules. Then they found that this can be used as an emitter, a single photon emitter, together with the atomic sodium as a filter, and they experimentally they got single photon signature of single photon homobundle deep. So these are some interesting works. Building from our previous interest, we have worked on this Raman current anti-stock Raman scattering, but this is a classical thing. We have developed some theory or nonlinear process QIQT3 for molecules. We driven by arbitrary pump and lasers. So the scheme is like this. So we have 3 lasers, and then followed by the 4th laser is a coherent anti-stock Raman scattering. One of the third order non-linearity is involved. And this is we're modeling this with real molecular potential, not just atomic level. So we model the absorption spectrum in a complex absorption spectrum. We've put in the vibrational modes, the laser spectrum, and these are all the necessary input. And then we got the emission spectra. So we want to do something like this for the quantum regime. Okay, for single photon. So now we start with this developing the theory, full quantum theory. Hopefully this is our origin. We want to include all the effects, polariton, cavity, many body, quantum noise, brown, electron phonon, power propagation. So far, we have got some of them, not all. Basically, we include this quantum Brownian. Is taking into account all the coupling between harmonic oscillators. So we model the buff, the phonon buff as harmonic oscillators. Okay, so this is based on this is a main part of the scheme that is based on this paper. We develop a unified and general theory to describe molecular system decoherence and relaxation pathways. the effects of radiative and non-radiative transitions on dephasing process are included. Means the molecule coupled to not only the radiation buff but also the phonon buff. And this theory should be applicable to condensed matter and to crystal especially, and molecular crystal. Okay. And it should be valid for non-Markovian reservoir. So here two electronic states, and we also include multi-vibrational modes because our polyatomic molecules have many modes, and each mode has, but each mode we assume as a harmonic oscillator. Okay, we assume to be all harmonic. We don't include any enharmonicity. So all the transition, possible transition, the main possible transition are included. So there are non-radiative transition that give rise to vibrational relaxation, and then the intramolecular vibration distribution. This is between the different modes, and also the radiative transition. The main transition is giving rise to the Franck-Condon process. And beside that, the first order correction is the Heisenberg-Langevin, which is the coupling between the vibration and electronic degrees. Okay. So based on this, we developed the theory, full master equation theory. And here the reservoir are phonon buff and the radiation buff. Here you have molecular vibrations and also electric system. So they are coupled vibration, and they're all coupled together, both coupled to the radiation and phonon buff. And if we write the Hamiltonian, the free Hamiltonian will be composed of the electronic, vibrational, phonon, and radiation. And all the V's are all the interaction with environment, and this is if you want to interact with the C, is also the cavity field, later cavity and the laser field also. So we have this vibration coupling, which is responsible for the IVR. And this is the system Hamiltonian electronic vibration, this phonon radiation. And then the coupling side, we have vibration, this, and then electronic vibration, phonon, electronic radiation as well. And this is the normal Franck-Condon, and this is the non-Condon Heisenberg-Langevin. Okay, is electronic vibration and radiation. So we put everything together, and then we trace out the phonon buff and the radiation buff to get the master equation. Okay. So in the usual case, in the existing literature, they consider they consider the ground and the excited potential energy surface to have identical shape. Okay, identical shape. In our case now, we don't have to do that, and also they consider each part of the reservoir, each part of the system interact independently with its own reservoir. That means we would have many reservoirs. Okay, but we find that this is not really true. Okay, so we make sure that all the different parts of the system interact only with one reservoir, single reservoir. Phonon, one single reservoir from phonon, and then another one with the radiation. That's all. And previously, they consider Condon approximation and also rotating wave approximation, and lamp shift was neglected. So all these we can relax all this approximation. We can include, we can have vibration relaxation, multimode vibration, non-Condon interaction, counter-rotating terms, and lamp shift. So now we have the general form machinery. So when what we need to study, we can switch on one at a time, so we can compare the effects. Okay, so this will be interesting for broad class of solid quantum materials like molecular F-center crystals, which includes the rare earth. Rare earth, we're interested in the rare earth, but it has been a lot been studied. So we now focus on mainly the molecule. Okay, for the vibronic radiation, which include the electronic vibrational coupling, the non-Condon part is due to the this first order expansion and higher order expansion. So this is expansion of the molecular coordinate in the ground state, and this is the expansion of the molecular coordinate in the excited state. So you have two terms here. So that's why here the diagram of this shows the excited state electronic, the ground state of electronic. So there are several physical process here to describe so we can understand. Here is all the counter-rotating term, non-energy conserving. Here are all the energy conserving. So here we can have the annihilation of the transition, but the vibrational can go up one step or go down one step. There are two possibilities. And in the same way, we have excitation in the electronic transition, but the vibrational can go up or go down also. So that explains why we have all these possibilities. So we put in all the equation, and then we trace out the radiation and the phonon bath, and we have all these Lorentzians. Okay, this is the dissipative and decoherence, the typical one. But beside that, we also have the cross term. The cross term comes from the fact that we have the linear, the Condon and the non-Condon term. So in the Hamiltonian interaction, Hamiltonian, we have one V here, one V due to here. So if you have the second order the master equation up to second order, the VV, then you have an interference cross term. That's how it come out. This has never been mentioned in standard literature. Okay, we found this, but we want to analyze further what would be the effect of this. Actually, the effect through simulation is not very big. It's quite a small contribution. Okay, and finally, the lamp shift term is computationally it is heavy. If we need the precision, we can go into this later, but we can neglect this for the moment because it can be absorbed into the atomic energy. I mean the molecular energy. Okay, the cross term can be generalized in this manner. A and B, the Lim-Blood operators would be where A and B are different operators of combination of the vibrational and the electronic operators. So we also have time integral due to the non-Markovian. So after developing the formalism, the simplest would be to compute the absorption and the emission spectra. Is given by this trace of the dipole moment metric element with the exponential of the electronic and electronic excited and the ground Hamiltonian. These are potential energy, vibration potential energy Hamiltonian. For the emission, normally it is written as a Fourier transform of the correlation function, but it can be shown that actually is equivalent to this form. The emission spectrum is reversed from the absorption spectrum. The order is different. The Hamiltonian exponential operator is different. Okay, then from the definition of the spectra, we also need to consider the phonon bar, the density or spectral density of the phonon bar. That depend on temperature T, okay, and also the spectral density. So the spectral density can be modeled. Okay? So if we engineer the surrounding environment, then we can engineer the spectral density, especially in the case of nitrogen vacancy diamond, and also all this dot spin in crystal. So we can control the coherence time through this spectral density. It is analog to the photonic crystal, where we are controlling the photonic density of states by controlling the quantum electrodynamics of the vacuum. So here the homogeneous broadening due to phonon bar is a typical is due to the phonon and the lattice of the solid medium, and the temperature dependent is included, okay, through this boson mean number. So we can describe the acoustic phonon effect by using this analytical expression that covers sub-ohmic case where S is less than 1, ohmic case S equals to 1, and super ohmic case. So this depending on the property of the reservoir, we can model by using this. Here you have sub-ohmic will be interesting for non-Markovian, while the super ohmic we can have a suppression of the decoherence. Okay. So here is the some simulation result of the spectra of diatomic molecule C carbon monoxide, the simplest one. Without, it means that CO has, in this case, we only consider one vibrational mode only. And we compare the effect of Condon term and the first order Herbert-Teller. So if you have just the Condon approximation is not very good, no good agreement. And if we include, then we will have a better agreement. The blue line is our simulation. So if you have a full expression that includes other terms, all these then we will have a better agreement to higher, all the more peaks will agree. Okay. We also study the effect of temperature dependence. So over the additional axis, as the temperature increase, we have the phonon, the lines are all broadened. Not only the temperature, but there is, because of the modeling of the phonon valve, there is a parameter cut-off frequency. So the cut-off frequency here, omega c, cut-off frequency will determine the spectra. So we have to choose the cut-off frequency carefully in order to fit in the experimental data. Okay. That is the something that is not satisfactory for theory. When we need to fit something, that means the theory is lacking. We need to improve on that. And this shows the almost symmetric case of the emission spectra versus the absorption spectra. So this is the normal case for the molecules. Okay, and the rest are these are the parameters. These are the parameters that we use in our simulation. Okay, now we go into the result for with polyatomic molecule with more than one vibrational modes, and the spectra has become much more complicated, and there's no harmonic, there's no equally spaced, because the modes are we are having on multi-modes. Okay, but the emission spectra is still has shorter wave, lower frequency or higher wavelength compared to absorption. So typically, this is the characteristic. So we can add in the terms non-radiative term, electron vibration phonon, then we can see the spectra become different. And if all the terms are included, then these are, we include more terms here, and then here we include almost more terms. So the spectra become different. So the electron phonon, here we have electron phonon. The contribution of electron phonon significantly increased the broadening of the emission spectra. So many peaks become unresolved. Okay, this is the spectra that where we compare and the effect of this cut-off frequency here. We vary the cut-off frequency for the absorption spectra. Here is the emission spectra. All terms are included. So these two are where we compare at a very large, somewhere here. The cut-off frequency is somewhere here, the largest. This is for the frequency range, and this for the wavelength. So both are reversed, frequency and wavelength. They're all in the normal. This nanometer, this is normalized. Here is the comparison of the emission and the absorption spectra versus the cutoff frequency. Okay. So now we want to go on with with the simulation by including the interaction with laser field, with the CW laser field, and then later add in the time-dependent laser pulse. And here are some preliminary results of the population of the excited and the ground state. It's not the simple nice curve like in the atomic case, because we are summing over all the states in all the vibrational states in the excited electronic state. Is sum over all the vibrational in the ground electronic state. And these are the corresponding coherences, the real part and the imaginary part. If you want to compute the population dynamics for each vibronic state is possible, we have to analyze one of the matrix element. Here we are already traced out. That's why it's all oscillation, rapid oscillation. Okay, so just to conclude here, I have shared the unified master equation for impurity molecule in phonon and radiation bath that will allow us to model molecular quantum information structure in a more realistic manner. So the unified theory, it goes beyond the existing approximation and include all these main dissipative and decoherent process, so that we can have a more clearer picture of decoherence and dissipative dynamics, because we want to use this for quantum memory. So we have to model the master equation in a realistic manner. We can't just use the wave function or the state wave function, even though it's density functional theory would not take into account the dissipative process correctly. And we have the non-condon counter-rotating terms all contributing. And we want to go higher order is also possible. And molecular lamp-shift also included. This will be useful for high precision spectroscopy later, and where short time scale is, in a case where short time scale is important. Yeah, we will include the different potential energy surface. We don't assume them to be the same. Okay. For the ground and excited electronic states. So we have the new master equation for molecule and that will really simulate the molecule in a more practical manner. Hopefully, the validity of our theoretical model can be verified with some experiment. So we can especially compare the theory and the experimental absorption emission spectra, at least for a simple molecule. Okay, and these are some references. Okay, so I will conclude here. Molecular quantum memory is a challenging problem, especially when we want to use it with existing scheme or combine with the best quantum memory scheme, so that we can make we can have a high performance quantum memory that satisfy the practical aspect, the scalability and all the practical aspect. Yeah. So it's more, hopefully more result can be reported in the near future. Thank you for your attention. Okay.
Thanks, Professor Ooi, for a really illuminating talk. The session is now open for questions.
Yeah. Thank you.
So if you questions, if anyone has questions, you may unmute yourself and ask.
Am I audible?
Yeah, please.
Okay. Thank you, sir, for this wonderful talk. Sir, actually, I'm a little bit curious to know about one thing. Just imagine there is a quantum repeater which is having two quantum memories, and we require a little high coherence time because we need to meet the end-to-end entanglement swapping. So I just thought, is it technically feasible that if we keep two quantum memories so that they keep on swapping their content and they can go on till whatever required time we want? Is it technically feasible, sir?
So you mean two quantum memories, you want to increase the storage time as long as possible?
Right, sir. Like one memory will give out its content in terms of photon and another memory will absorb it. Then again, it will give it a photon to it, like to and fro, like the content will move till the time we want. Is it technically feasible, sir?
I see. So you mean like connecting the two quantum memories in series. So the output from one quantum memory will go into the as an input of the subsequent one, right?
Right,
Yeah.
sir. Exactly.
Yeah. Because it's I'm not sure if there is any advantage of doing that, because each time we pass through the quantum memory, we have a risk to 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 lose the information unless the second quantum memory serve as a kind of reverse is, it will reverse the the, the loss of fidelity or any, that means if this can only be done if the two quantum memories are correlated. If they are correlated, then maybe we can passing through a series of quantum memory may give some improvement in the final output. Yeah, that would be a
Okay.
good idea to do some simple study. Yeah.
Okay, sir. Okay, sir. Thank you so much.
Thank you.
Thanks. So any other questions?
So, I have a question, sir.
Please.
Thanks for the talk. Sir, can we use quantum dot systems as a quantum memory device?
Yes. Quantum dots have been studied as one of the candidates for quantum memory, but I did not include it because somehow uh, it is not so maybe not as widely being used compared to the atomic gas. But it is possible. Quantum dot is possible, but normally quantum dot is being used to produce a single photon source. Yeah. So, but if quantum dot, you can make many quantum dots. So it's as artificial atoms, and then I think it will represent something like the ensemble atom. Yeah, it is possible.
Okay, okay. Thanks.
Any other questions? One last question, maybe. Okay, if not, let's thank Professor Raymond Ooi again for a really illuminating talk.
Professor.